Okay, so this is for 4305 lab for the fall of 2021. This is lab 2, the programmable square wave. So in this, we have a couple of inputs. We could see these 4 switches right here represent a 4-bit input, which is M, we'll call that, and that represents the on time of the square wave. And then we have these 4 switches right here, which represent the 4-bit number of N, which represents the amount of time off. So based on the constraints of this lab, we'll have M times 100 nanoseconds and N times 100 nanoseconds. And that's what we should expect of the output. So if we have M as 1 and N as 1, then we should see 100 nanoseconds on, 100 nanoseconds off, and repeat until the user changes the value. So to do this, we have a modulus counter, which goes from, counts from 0 to 10 pretty much, or 0 to 9, and that acts as a clock divider for our square wave generator, and that will give us our 100 nanosecond clock, which would simplify the multiplication based on these signals. So right here on the screen, we can see Vivado's ILA IP. So this will allow us to see the square wave output from the viewpoint of the FPGA. Okay, so to start, we have our edge cases right here. So just to avoid any ambiguity, I made it so that the square wave generator only gives an output if M and N are both not non-zero values. So if M is 0 and N is 1, still no output. Also vice versa, and if they're both 0, then we're not going to have an output. This LED right here will let us know if there's an output. I can run all the edge cases on here, but I thought it'd just be easier to have the LED show us that for real quick simulation. Okay, so now let's do the simplest case where we have M and N are both 1. We can see that the LED is on, so there is indeed an output. So if I go on to Vivado's IPA or ILA and I run it, we can see that we do get a square wave output. Now the ILA in Vivado will only count the amount of clock ticks. So here we can see that there was 10, or it says 10, but that's based on the input clock. So we could see here that this is actually supposed to be 100 nanoseconds, but it only does say 10 here, so we don't really have to worry about that. And based on this, we could see that we have 120 in this case goes to 130, and that represents our high level, which is a distance of 10, so 100 nanoseconds. And then from 130 to 140, which is also a distance of 10, so 100 nanoseconds. Okay, which is exactly what we expect because M, the on signal, is 1, and N, the off signal, is also 1. Okay, so now let's do a case where M and N are not equal. So I'll do where M is on at 6, and then let's do N is at 4, so we should expect 600 nanoseconds on, 400 nanoseconds off. So if I run this on the ILA, we could see that right here we have starting at 118 to 178 is a distance of 60, which is what we expect because our on is at 6. And then we should expect a distance of 40. So from 178 to 218 is a distance of 40, hence why we get the value of 400 nanoseconds. Okay. So now let's do an edge case just to further prove this point. So let's have on be 15, so M is 15 and N is 1. So we should expect a really long time on and a short time off, which is exactly what we get here. And then let's flip this to see the other extreme. Actually, let's do this. Oops. Okay, so now we should expect a really long time off and a really short time on, which is exactly what we get in our output. So this concludes the lab for, or demo for lab 2.